So this is the joint work with Amit Churasia of SDC, and also Bernard Minster of SIO, and also in collaboration with SCEC and Philip Macklin and Tom Jordan of SCEC, Southern California Earthquake Center at USC. So this is the group, High Performance Geocomputing Group at SDC, and funded by SCEC and also NSF and Exceed program. Sorry. Now talk a little bit about, so this talk is about the seismic modeling. And the seismic modeling has always been a data-driven science, but now it's shifting to the data intensive like many other applications. What my focus here is about the parallel I/O environment, and talk about the data storage and checkpoint, the format, and transfer, and also the visualization part. So first, we want to look at the computational requirement in terms of the seismic computation. And then we typically see 3D ratio of physics box to the grid spacing multiplied by time steps. This is together, we call it the computational requirement in seismology. If you look into this chart, over the past some years, it has been improved a lot, and roughly 3 orders of magnitude we have accomplished to meet the seismology requirement. But we still have a long way to go, and we need another 4 orders of magnitude to jump up to meet the requirement, particularly for engineering requirement, and for wall-to-wall kind of simulations at the frequency up to 10 hertz. So, and that will be also associated with the data requirement, as you see for the tomography and the intensity measure, data intensity like simulations. So let's take a look at simulation, sorry, and I think. I made a simulation we did in 2010 as one example to show the capability simulation where we stand now. And this is to propagate ground motions up to 2 hertz for a wall-to-wall rupture of the entire southern San Andreas fault. And what you see here is the rupture directivity and coupled with the basing effect that increase the seismic risk, particularly in the Los Angeles area, major simulations. So if we look into the comparison here with TerraShake and M8, and this both are the milestone simulation done here, enabled here at the SDC and at UCSD. So the TerraShake we did in 2004, and that was using the data star, and at that time running for 5 days, and produced 45 terabytes output. That was a record simulation in terms of one single simulation. And so the data was archived to the HPSS, and at that time was the largest high-performance storage system in the world. And we had more than probably 30 people from SDC supported for this project. It was a masterpiece, and showing how we can support and those kind of simulations at a very large scale. The M8 simulation was 2010, running on the Oak Ridge on the Jaguar system, and using 223,000 cores running for 24 hours. And what you see here, things changed. The problem size is much bigger, and we had to decimate lots of data size to get into the parallel file system. And what particularly different here is because the system at that time from the Jaguar will barely survive for a few hours. So we had to keep writing checkpoint to the file system. So that is roughly 32 terabytes data for a single time step. That will challenge both the last year file system and also the applications scalability part. So this is a project from SCEC working now on, and called CyberShake, and this is to use a waveform-based intensity measure relationship to calculate seismic hazard. So currently it's working on the Los Angeles region map, and it's now moving to the state-wide map. And so what you see here, it will require lots of computing hours. So we are now getting a GPU code now ready and to replace this CPU code is going to save 100 millions of CPU hours. But the challenge remains with the data part, and because here you have to deal with the billions kind of post-processing jobs, and that's currently SCEC is using the Pegasus workflow to do it. And also there's more than petabytes of stored data and how to handle it. Another project is the tomography, 3D tomography project, and also from SCEC. And this is to improve the velocity model, and very important for the accuracy of the application. And so this is now already generated petabytes data. And actually, for this project, particularly challenging is transfer data between different sites from DOE and NSF sites. So I want to show you one example how we handle with the parallel I/O and at the runtime. So typically the data, community data input is terabyte size and fragmented, also scattered, not in the right way. And what we do is we use the contiguous block read and also using point-to-point communication. So this is kind of trade-off between communication cost and I/O cost. That works very well. And aggregated the writing we use in the reverse way and to do the same work. And for checkpointing, we write using the EDIOS library to separate the metadata with the I/O library. So for protection part is using the parallel MD5 checksum, and error detection is through the workflow, and also with Globus Online for data transfer. So this is another project now going on with I/O library and with SCEC, and this is to develop an I/O library so that you can use it by by the community's seismologists. They do not need to worry about I/O part. We will worry about we will take over about I/O issues and how to handle with the file systems. So this is the web service part from the SCEC as one example. And the visualization is another important part. This is work from Amit Chulasia, my co-worker from SDC. And what he shows here is about 3 parts. One is about use ray casting to performing volumetric rendering. The second is using Graph-C tools, and that's to encode the vector and the information. That's used also the KRT's star cave. And the third one is now in situ visualization is now under development. And we work together, already show the case and to run on the heterogeneous computing environment, running the server on the GPU side, running and the in situ visualizing on the CPU side has been very good. So with that, thanks very much.